Hello, everyone. I think this is already the second to last lecture of GR, and we are in the middle of exploring certain consequences of Einstein's field equations. One of them are gravitational waves, and I mentioned last time that there will be an exercise series this week where we will do some calculations, essentially deriving the form of gravitational waves. I already gave you an overview on what is going on in this derivation, but I leave the calculation to you, essentially. But today I would like to give you some additional information also regarding the measurement of gravitational waves. By the way, I should mention that the exercises should really be regarded as an integral part of the course. I realized that when I got the feedback from the lecture evaluation, that some of you may not be aware of the fact that during the exercises certain concepts are maybe not introduced, but at least somehow explained it's explained how they work in practice there. So that's something I usually don't have time in the course. And it's important, of course, to also know how to apply all the notions that we are introducing. So in this sense, you may, of course, follow the course itself, and probably would know already a lot about GR, but to really get a feeling of what it means to actually, let's say, solve the Einstein equations, to understand consequences, it's useful and strongly recommended that you do the exercises. You may also just, if you're too late for that, just read them and read the solutions. That may already be quite instructive. But this is just to make clear that this is really a part of the course. It's not just an add-on. It's considered to also convey basic messages and basic material that you should learn. Okay, so back to gravitational waves. So colloquially, they're sometimes called just ripples of space-time that propagate. And that's maybe I would say, accurate description if you know what that means. And of course, you now have all the tools to understand what it means. And what it really means is that if you consider the metric is itself subject to an equation of motion. And this equation of motion looks now like a wave equation. So what does that mean formally? I'll just reintroduce some notation from last time. Just to recall, we had this eta. Eta is the flat metric. And then we have the deviation from the flat metric, which I called, in this particular case, hij. This is the notation used also in the exercise sheet. This you should see as the part, there's no physical distinction between this and that. The distinction is just in our ability to solve it. So this is something that is considered to be exactly solvable. And of course, we could say, if we have no matter, one of the solutions, the trivial solution, is the flat metric. But you could also here replace this eta ij by another analytically known solution, such as the Schwarzschild solution. And then this h is the part which is, first of all, has to be small, but it usually is such that you cannot solve it exactly. That's why you separate it from the left-hand side. And so in our consideration, we just chose as an example flat space-time, but you may also choose any other space-time, for example, the Schwarzschild solution in which we live. We are close to Earth and close to Sun, and then add gravitational waves onto that. And this is not completely true, but for most space-times, you can just add gravitational waves on them. And all the equations that we are now considering are very similar. Of course, sometimes this metric enters, and this has to be taken into account. Anyway, what you will show in the exercises is that the equation of motion that essentially governs the behavior of hij is given by this equation in an appropriate gauge. So a gauge is a choice of coordinate system, and I mentioned last time that we can somehow do, as always, as often at least, we can try to choose a clever coordinate system. And in this particular case, in the case of the treatment of gravitational waves, it's useful to just use this freedom to make sure that certain terms that it would initially have for an arbitrary choice of the coordinate system, that they disappear. This is very similar to when you solve, let's say, Maxwell's equations. Maybe you remember from your course in electrodynamics that if you, for example, solve for, let's say, the A field is the vector potential in electromagnetism, then you still have this freedom, this gauge freedom in electrodynamics, and you can choose, for example, the Lorentz gauge. And in the Lorentz gauge, the wave equations look very similar. Here is also something called the Lorentz gauge, and in the Lorentz gauge, the wave equations look like this. Generally, the expression looks more complicated. So in the exercises, you will first derive the general expression and then make this particular choice of coordinate system, and then show that in this particular coordinate system, it looks like this. So just to be sure you understand what this means. So this is really just the ordinary D'Alembert operator, of course, for that coordinate system choice. And of course, one has to make sure that this choice of coordinate is such that that we understand what this eta means. But of course, one may choose a coordinate in which still it has the usual form of 1 minus 1 minus 1 minus 1. Okay, so that's essentially what you will derive in the exercise. I just take this as given for the moment and refer to this exercise sheet of this week. And maybe I'll also make a remark just to make sure you can make the connection to the exercise sheet. It turns out to be convenient to introduce another quantity to represent h. And this other quantity is called gamma. It's also a tensor with two indices, therefore, and it's defined just as hij minus 1/2 the eta metric times the trace of h. So if I just write h without indices, what this means is that I take, maybe we should take upstairs indices, I take the trace, and trace is multiplying with the metric eta ij. This is all in first approximation. So in principle, if I would calculate the trace of a tensor, I also have to put here the metric, and the full metric is of course not this eta, but it would be eta plus h ij. But because we already have here a term hij, this would give a second order contribution, and we are just only considering linear contributions in this first order perturbation theory that is sufficient to treat gravitational waves. And actually, as I will mention in practice, if you, for example, want to calculate real gravitational waves as they are detected on Earth, this is just an incredibly small term. So the squares of that are so small that you can really safely neglect them, at least as far as I know, for all the current observations that would probably be irrelevant. I should say, in the far field. So now I'm talking about the region where we detect the waves. At the point where they are generated, there are, of course, enormous fluctuations, and they can no longer apply perturbation theory. So maybe I should make clear that if you talk now about gravitational waves, you should again understand it in the same way as in electrodynamics, when we have radiation and we have this far field limit. And in the far field limit, the electromagnetic radiation has a nice form. It's kind of a plane wave approximately, and so on, or a radial wave. And then close to the antenna, the behavior is much more complicated. And here we are in this far field limit. So we're talking about the region where we are detecting them and not the source of the waves. Now, okay, obviously you can see that this quantity here carries, or the quantity gamma carries the same information as h. It's just somehow a different representation. And it's sometimes called the reversed trace form of it. And the reason for that is that if you take the trace of gamma, so I will just make this as a bracket here, if you take the trace of gamma ij, then, okay, on the right-hand side, you get just h, if you take the trace of this. If I take the trace of this, I get minus 1/2 eta ij upstairs, eta ij downstairs. And you know that this is just essentially the trace of the metric squared, which is 4. It's just a dimension. And then obviously the whole thing is just minus h. So this just shows that the trace of the gamma is just the opposite of the trace of h. And in the calculations, you will see that this is useful as a representation. But I'm just saying that to make clear that for the moment, you can just think of this object almost as h. And this is the transformation rule. So if I tell you now something about gamma, you can easily go forth and back. So if you really want to know the real metric, you have to translate it back to h by making this subtraction here. Okay. Now, the last thing I want to take from the exercise series, so today I'm kind of drawing a lot from what you're going to do in the exercises, is an explicit expression of this gamma tensor for the case where you have a source somewhere. And what you get here is the following. You get an integral over something that decreases very fast, and then Tij, this is the tensor, this is now the source itself. But remember, we are far away, so you should think of this term being very large, and I integrate over the region here of the source. So let me first write it down and then maybe give further explanations. T minus x minus y, these are this, with the underline should indicate they are understood as the 3 vectors, and then comma y. Right, this is also the 3 vector. That's the expression. And this expression looks very similar to expressions you should have seen in electrodynamics, which is not a surprise, because all I'm kind of saying is that we try to solve this equation here in the far field limit. And that's what you have done in electrodynamics, exactly. Because in electrodynamics, you had this. Now, of course, this H has a different meaning. In the electrodynamics, it was maybe the electromagnetic potential, but at the end, it was an equation of that form. And therefore, it's not surprising. I mean, it has to be the case that up to constants, of course, it's the same thing. Oh, actually, I forgot to say something. This is the form if you have no matter. Now, if you have matter, then on the right-hand side, you have, of course, the energy momentum tensor. And to derive this in the exercises, you will have, you have to introduce the energy momentum tensor. So maybe I was now saying two things. So in the if you are, I mean, at the point where we are detecting the waves, we are neglecting the matter that is here. So we're just saying far away or in the vacuum, the wave propagates according to this equation. Now we take into account the source, and in that case, you would have here on the right-hand side essentially some additional expressions, as we will see in the exercises, and then you will get this expression here. Okay, now what does this expression tell us? So first of all, it tells us that somehow the strength of the let's say, deviation of the metric. I mean, gamma is essentially the deviation of the metric, as I said, because it corresponds to this h, decreases with 1 over r. So it's a bit like a potential in that sense. Or like, I mean, the behavior is the same as for, it's just a 1 over r behavior. If you think here of the source as being something small, then this integral only has to reach over the part which contains the source. So if you have far away in space the source, this y here, this is a spatial y, this just goes over this region of the source. And therefore this x minus y can be approximated by essentially just, I mean, this is the distance from us from the source, but we can think of this, for example, here as just being 1 over r, where r would be the distance from us to the source. So in that sense, we will at the end not have any spatial dependence on small scales. So if you, this x here, maybe I should also underline this x because it's actually here we really make this distinction between time and space. So this is the time variable, and these are the three space variables. And this whole expression doesn't vary a lot in x, because if I move here by a few meters or even a kilometer, this doesn't change this quantity here, really my distance from the source, in a noticeable way. And therefore, we can just, and will do that, think of this as something that mostly depends on time. But the time will, of course, be important, because you see this expression here corresponds to something that in our units, where c is equal to 1, propagates with the speed of light. Why is that? So think again of y being very small compared to x. So let's, for the moment, just think the source is even just at y equals 0. Then you have here just t minus the absolute value of x. This means that if you want to know what is here, let's say, on Earth, the momentary ripple in space-time, so the amount of the change of the metric, then what you have to do is to evaluate something, some property of the matter of the source at the time t minus x, which is, of course, exactly the time you would get by going with the speed of light backwards to the source in time. So that's what it means that the signal essentially propagates at the speed of light. That's this expression. But I will not further comment on that, because the whole discussion will be just exactly analogous to the discussion in electrodynamics. What I want to do is to talk a bit more about how we actually detect these waves. And you may know that the detection of gravitational waves is enormously difficult and has only been achieved a few years ago. You may have heard the news, maybe it was just before you started to study physics. And what I now want to try to do is to explain to you what it means, what is really the observed phenomena. How can we turn this gamma, which is still an abstract quantity, into something that we can measure? But for this, I would like to make a simplifying assumption, which is not entirely true for this. I mean, it's not true for the source that we have really detected. The source we have detected is, as I said last time, is an event where two black holes essentially spiraled around each other and then merged. And this is a complicated process where you have many frequencies. But let's for the moment assume that the source is something that just turns at the fixed frequency. This would, for example, be the case long before the spiraling down. So if there are just two black holes that move around each other, they would probably, their frequency would change, but only slowly. By the way, the reason why the frequency changes is mostly because as they are moving around each other, they are also, according to what we are just now discussing, emit gravitational waves. And gravitational waves, of course, carry energy. So they lose energy by being a source of gravitational waves. And when they lose energy, their frequency will, of course, change, and they will come closer to each other and eventually merge. So the frequency changes and over time, but let's for the moment just assume that we only consider somehow a time interval where the frequency doesn't change too much. And then it's clear, then you know what will happen. If you have a source that has here a behavior, so this t is the behavior of the source, has a frequency omega. It's something, some tij times some periodic function, so some cos omega t or sine omega t. Then, of course, I will have the very same periodic behavior on the left-hand side. That's also something you know from electrodynamics. So roughly speaking, we could say that what we find, or what we'll have for a source with fixed frequency, and I'll make another, not really an assumption, but a choice, choosing a basis in which tij is diagonal. So this may also, of course, change over time, but I will just assume it's essentially an object that just rotates in a fixed manner, so it doesn't change its shape and so on while it rotates. And in this case, Tij is of course a symmetric tensor, so we can always find the diagonal basis. And then Hij must have the following form. So it's still a function of t and x. And now you see I make the move here from gamma to h, because up to a constant that is added here, I mean a constant trace, as you see here, the behavior is similar. So if I have a periodic behavior here in h, or conversely a periodic behavior here in gamma, I will have the same periodic behavior in h. And I'm now not interested in the details of this periodic behavior. The only thing I'm interested in is to say that, of course, it will have different terms in the diagonal. And let's call the first term h0, that would be the amplitude of that, and then some periodic function. So if it's something that turns uniformly, then I would have cos omega t, something like that, up to a phase. But let's just assume the phase here is 0. Then I would have here another term h1. And then because I already chose the phase of the first one to be 0, I can no longer assume it's also 0 here. I mean, I can choose the one phase by just choosing the 0 point of the time t, but I can only do it once. So here I have still something like omega t plus some phase, which I call phi1, some offset, which it rotates. And then the next term is something like, I mean, this is the other diagonal. Okay, now I have troubles writing a big diagonal matrix here, so let me try to put it here a bit down. So the next diagonal entry is accordingly something like h2, some other amplitude, cos omega t, it's always the same frequency, plus another phase, phi2, and the last term is something of the same form. Okay, even if you cannot read it, you know what it is. It's just the same form with a 3 everywhere. And we assume that this matrix is diagonal. Okay, so what we learned from that, or what we know under all these assumptions that we made, is that we can think of the metric as something that, first of all, is essentially the flat metric. So remember, this is only the deviation from flat, but then up to the flat part, so up to the 1, which would be here, we have a very small h0 times cos omega t. So there's this small fluctuation in the metric. Okay. So now we have to, I mean, we have to remember, and that is now an instance where this is really relevant, that everything we are doing is, of course, depending on the choice of coordinates. And we already made a choice, namely the Lorentz gauge that I mentioned before. So this is a particular choice of coordinates. And it's not at all clear that this choice of coordinates is such that, for example, a straight line in the coordinate system is indeed a straight line in real space-time. But it turns out it actually is in this particular case, and let us verify that. So let's look at the following, because that will be useful. So let's suppose we have let's see, okay, maybe I first draw a diagram. So let's suppose we have here a spatial direction. Let's just look at the spatial direction x1, and here the time direction x0. And now I could just say, I want to consider a world line of a particle which, as it crosses time equals 0, here, it moves in coordinates just such that the x1 coordinate doesn't change. So in other words, I could say there's this, if I call this world line gamma, let's call it, for later reference, I will call it gamma p, because p could be a point somewhere. So p is just a point in space, and let's suppose the world line of that point in these coordinates is just straight up, which means that in coordinates we have some curve parameter. So let's see how I should call that curve parameter. Well, yeah, let's maybe just take the eigentime tau, and then the curve parameter will be mapped to some, okay, here I think it's useful to call x0 also t, just to make, because here we have really a distinction in some way between time and space in the sense that we treat, I mean, we want to have a source that varies in time, but not in space. So having this notation that x0 is t, I could say, of course, this particle moves in time. So there's some t depending on tau. If I had chosen nice coordinates, I could choose coordinates in which t is just equal to tau, but the coordinates are already given. So I just assume that it's something, some t that depends on tau. I'm not further interested in this t, but I, of course, want that it somehow moves up. But moving up means all the other coordinates are 0. So that's in coordinates. So that's kind of gamma 0, gamma 1, gamma 2, gamma 3. That would be the notation. That's the general notation, just to make the connection here. So that's a coordinate straight line. But is this really a straight line in real space? So let's check that. How do we check that? So we just have to remember the geodesic equation. And the geodesic equation tells us that we have to take the second derivative of the coordinates. And actually, let's just look at coordinates now 1, 2, 3. I'm only interested in seeing how it deviates in space. I'm not interested in how far it moves in the time coordinate. So then the geodesic equation for any component, that's also true for the 0 component, but I'm not interested in it, is this one, gamma I plus the gamma symbol I and summation over jk. Here I have to sum over all 4 possible values of these indices, gamma dot j, gamma dot k. Now, because we start, so I just look at the starting point and see how the deviation is there. And of course, I could then repeat the procedure at any point, because I start with a line in which only gamma 0 dot is non-zero. We can neglect all terms where j and k is non-zero. So this just follows from the above. Maybe I'll write it here briefly. Of course, gamma dot is just something here. So here I'm not interested in some t dot tau, but then 0, 0, 0 in coordinates. So that's the coordinate way of thinking. And therefore, we can write this as gamma dot dot plus the gamma symbol I 0, 0, and then here something like gamma dot, now this has to be a 0 as well, gamma dot 0, gamma dot 0. Okay, now there's only one gamma symbol here. I mean, actually 3, because I could be 1, 2, or 3, but there's that's easy to evaluate. So gamma I 0, 0 is generally given as follows. You hopefully remember the definition of the gamma symbols in the Levi-Civita connection, which I'm using here. So it's first of all, I have a G, an inverse metric with indices upstairs, and then I have to sum. And because I'm only interested in the 0, 0 components, this sum looks like this. So the L is the summation parameter, G L 0, 0 minus G 0, 0, L. Now, because I'm only interested in I equal 1, 2, and 3, J L will also be only 1, 2, and 3, because this is diagonal here. If the metric is diagonal, then also its inverse is diagonal. So I can restrict myself to L also being in 1, 2, 3. What does this imply? This implies that, first of all, this term goes away because the matrix is diagonal. So the entry 0 something, non-zero simply doesn't exist. Don't even have to care about the derivative. The same for the second term. And the last term is also 0 because we assumed that in the metric, the spatial dependence disappears. So remember I said here that this thing in our approximation when we are far away does no longer depend on x. And of course, if the deviation from the flat metric doesn't depend on x, then also the total metric g, maybe actually I should write the total metric g is of course this thing here. That's the total metric eta plus h. So if this thing does not vary fast in dependence of the spatial point, then the same is true for this. So we can also, in our approximation, assume that this term here is equal to 0. So which is nice, because this all tells us that, yeah, actually, I see I forgot here an I. Sorry about that. So here is a gamma dot I. But this all tells us the following, that the geodesic equation reduces to the part without the gamma symbol. So we have essentially shown the gamma symbols just disappears in the part that is relevant. And so we have only gamma dot dot. And therefore the geodesic equation is just gamma dot dot I equal to 0 for I equal to 1, 2, or 3. Okay, what does this mean? This means that indeed such lines here, coordinate lines, let me now complete it, are actually geodesics. And this is independently of where they are. So I could have another coordinate line. Let me put it here. Let's maybe make use another color. It could be another point. Let's call that point Q. And that could be another, that has another world line, gamma Q. And this world line would be something like tau maps to, again, t of tau. Maybe it's a different t, and call it t bar. And then wherever it is. So I think I have implicitly assumed before that this is the point here. Yeah, I think I have implicitly assumed before in the drawing that here we have x1 equals 0. Okay, this is a bit ugly. Let me briefly redraw this diagram, otherwise it's really not nice. So in our diagram, we have one world line, which is essentially a world line at the point 0. So that would be the blue one, or the bright blue one, and then the dark blue one is the one at some other point. It's the one here. And this would be gamma p at the coordinate where x0 is equal to, x1 is equal to 0, and also the other coordinates. I'll write it fully. Could be a point at x vector being 0, 0, 0, and then the other point q, gamma q, is at x vector equal to, let's say, 1, 0, 0. 1 is just some value for the coordinate here. Here is 0, here is 1. Okay, I hope you see the idea. So we have just two world lines, and we have now established that these straight lines are also geodesics, which means that if I had a real object here, which I put in coordinates somewhere, so I fix it in coordinates for some reason, then it also stays there. But of course, I should think the other way around. If I have an object that I place somewhere and it's freely falling, then in the coordinates that we chose, it will indeed just stay at the place where it is. And this is true for another object. So why am I interested in two objects that are close to each other, or that are somewhere? So, as I said before, we want to understand the detection of gravitational waves. And this is now, I think, the key point. So let me redraw the diagram just on a slightly different scale. so we have here again the same diagram with x1 and x0, and we have two objects, the point P and the point Q. I now draw them much closer together, but think of them now in the following way. So maybe you have seen pictures of the gravitational wave detector, and this wave detector consists essentially of a lab, which is at the point P, then a long tunnel, which connects the lab to somewhere else, and here is a point Q. And maybe there's another tunnel, I'll put it maybe downwards here. This is a second long tunnel. By the way, these tunnels are in reality maybe of the order of 4 kilometers long. And here would be another point, let's say Q prime. And here is P. Now I'm only talking about P and Q. And we can indeed, for the moment, safely neglect the Q prime. I will tell you that the Q prime is actually not absolutely necessary, in theory at least. In practice it is. And the reason, as I will see, is that we don't have very good clocks. So we need essentially the other thing as a clock, so to speak. But for the moment, just forget about the Q prime. Just think of two places which are connected by a tunnel. Now let's suppose that we somehow are able to put in this lab a little object, and here another little object. Actually, these will be mirrors, which for the time that is relevant, which is very short, so the time that is relevant is maybe the time that it takes for a light ray to come and to pass from P to Q and backwards. So let's suppose that we can assume that these points are actually freely falling. This is, of course, not the case in reality. They will be mounted somewhere or suspended somewhere, but let's just assume that for the moment. And this assumption is a good approximation of what's going on, because an object that, even if it's suspended somewhere on very small time scales, and this is, of course, a small time scale, the 4 kilometers for a light is nothing. It's as if it was freely falling. It will not be able within that time scale to actually get any forces from the outside that moves it that are relevant. And indeed, actually, the much nicer way to measure gravitational waves would have been to have here labs in free space. So this would just be a satellite, and this would be another satellite. And of course, the satellites are clearly freely falling. At least a good approximation. They still have a finite size and so on. So that's the much better thing. This is just much more expensive. This is the next stage. There is a project planned at the moment where, let's say, the next generation gravitational wave detectors are actually based on satellites. So actually for the theoretical, let's say, investigation that we are currently doing, it's maybe even nicer or clearer if you think already of these labs as being these satellites rather than mounted on Earth. Because Earth, the actual mounting really has no bearing on the, I mean, of course you have to deal with noise and all that, but this is not anything relevant. So it's not that we kind of measure, let's say, the stiffness of Earth or anything, because that would propagate at the speed of sound, which is much too slow to have any impact. So really think of freely floating labs. That's an important point to make, because that can be quite confusing. So these are freely falling labs in our assumption. And if they're freely falling, we have now established that in our coordinate system, their coordinate lines, their world lines, look like this. Now what a gravitational wave detector does is to somehow figure out, of course, whether there is a gravitational wave or a change of the metric. Now this looks, now if you didn't know about GAR, of course you do, this looks kind of hopeless, because here these are just two world lines which stay at the same distance. But of course you know that this is not the real distance here, this is just the parameter distance. And the parameter distance is actually completely irrelevant for anything physical. You cannot measure it. That's just a choice of coordinate system. What is relevant is, of course, the real distance as given by the metric. And the way to measure the real distance is to just have a light beam being reflected between mirrors at these two places. and measuring the time it takes for the light beam to return. So that gives you a measure of distance, which is now a measure of, which of course now includes the metric. So what's the distance in this particular case? So we are here interested in the distance. And of course, if we measure, as we are now used to distance in terms of times, we don't need to worry about units. But the distance is obviously in the x1 coordinates given by just first of all 1, because the eta symbol of the metric is just 1. So maybe I'll briefly show again the metric. So the metric we have is this one, but that's just a deviation from the unit metric. So we have this 1 here. And then we have this deviation h1 in the first term. And if the coordinate here is just the x1 coordinate, so we're measuring a spatial distance in the one direction, we only have to consider this term here in the metric, the h1 term. So what we get as a expression is that the distance is given by some h1, which will be a very small amplitude, and then cosinus omega t plus some phase, phi 1. So this is the distance between P and Q. And of course, if we now, by the way, go back to this and say this is the x1 direction and that's the x2 direction, we could do the same for the distance between P and Q prime, and it would be 1 plus h2 cosinus omega t plus phi 2. Okay, so what do we now really measure? So suppose first of all that we had perfect clocks or extremely accurate clocks. Then, as I said before, you wouldn't need this second arm of the so-called interferometer. So you would just need that arm here. So you would really just do this experiment, you reflect the light beam and measure when it returns. So you essentially measure the time, let's say, between these two events. And this time will, of course, be proportional, or in our units where c is equal to 1, to exactly that thing here. So this time will sometimes be a bit longer and sometimes be a bit shorter. By the way, this omega for the real gravitational event that was observed is of the order of, I think, between 50 and a few hundred hertz. So that's something that changes actually quite slowly compared to the distance the light travels. So you can somehow in first or zeroth order assume that the light returns long before there was a change due to the time progressing here, because this omega is just so small. But you just measure this distance over time. So you plot some graph at the end, which has here time. This is now an ordinary diagram that corresponds to a measurement outcome. And here you essentially plot the distance. And this distance will now be roughly 1, because we chose the coordinate to be 1. But in reality, it could be 4 kilometers or so. And then you will have some fluctuations here. Then you could have another, yes. So that's what you would measure if you had a precise clock, because then you could measure this distance precisely. And that would be the evidence, or let's say the observational implication of a gravitational wave. You would see that these times the light needs to return here vary. Now, in reality, we don't have clocks that are so accurate that can measure the time precisely enough to really understand when this returned. But what you can do is to measure very accurately relative times. So think of the second detector arm now. And of course, the second detector arm will also have some distance PQ prime. And because of the different phase, see here that there's a phi 1 here and a phi 2, and generically they will be different. We may have something that maybe looks like this. Okay, I'm not very good at drawing, but you see the idea, the relative distance changes. So what you have to do is to send a light beam the same, or to split it somehow, send one half of the light beam into this direction, send the other one half here. Both are reflected, there are mirrors here and here, and then measure which of the two light beams arrived first. The difference between the two will still be enormously small. You may have heard in the news when gravitational waves were detected that the actual shift here in the length is just of the order of 1/1000th of the radius of a proton. So that's really an enormously small distance. And you see, when you travel at the speed of light, the time difference is even smaller. So it's enormously difficult to measure this, but with and this is where quantum technology, by the way, enters. With quantum technology, this is possible. So there are methods to really, I mean, obviously that has been used, and that was the main, one of the key features that was needed to make this experiment work. You can somehow measure time differences or length differences to this enormous precision. Okay, I think this is essentially what I wanted to tell you about gravitational wave detection. Maybe I just briefly recall that we research or science or our, the whole scientific enterprise was kind of maybe in a lucky situation that it's just at the boundary of what is possible at all. I told you that there is an enormous energy that is dissipated when two black holes merge. It's of the order of 3 solar masses. So that's is just, so the whole burst of gravitational waves just lasts for maybe a third or a fourth of a second. And if you calculate what the power is of that, then it's of the order of 10 to the 49 watt. That's a pretty good light bulb. But of course, the energy is actually emitted mostly in terms or in the form of gravitational waves and not in light. So this all goes into gravitational waves. But because this whole event is of the order of 1 billion light years away, they have been enormously attenuated. So despite this enormously, so we were kind of lucky, it's an enormously energetic event. And then the distance is, however, so large that what arrives here is so small that the ripples in space-time are such that over a distance of 4 kilometers, length just changed by 1/1000th of a proton radius. Still, this is just the limit of what we can achieve with current high-precision quantum technology to measure distances. So this was all really at the edge of what was possible, and it's in some way really fantastic that this worked at the end, so that we could do this. It was progress not only in gravitational physics, but also, I think, in measurement metrology, measurement technology. Okay, now I think it's time for a break. I would like to reconvene at 5. Are there any questions you would like me to answer?
Yeah, there is a question from Yona. How can we get the energy density of the gravity waves out of the metric perturbation age?
Oh, yes, that's a very good question. How do we, at the end, turn this whole thing again into an
if we can, actually.
Pardon?
If it is possible, actually, that was the question, I guess. And if yes, how?
Yes. Okay. I think, I mean, the main thing what we are doing is essentially, I mean, in reality, or maybe you have even seen the presentation that was given last week as an extra tutorial. And at the end, we are trying to somehow determine the energy, first of all, that is dissipated in total. And of course, for that, we have models. Okay, maybe, okay, there are 2 ways to answer the question, and I'm not sure. Let me give both of them. So one is, of course, a kind of direct answer. We could try to associate to the gravitational field some energy. This is, in general, difficult because the question is, what is the reference point? I think I mentioned that already, that in general, we cannot kind of bound or let's say single out the region of space-time and say that's the energy that is in this space-time. However, in special cases, and let's say in this linear approximation, we can somehow even understand it in almost a Newtonian sense. But I think that maybe more, let's say, defining the energy that is contained in the geometry of space-time is inherently a subtle topic, and it really depends on definitions, and it's not clear whether it's something that is directly measurable. But the physics question that has a very clear answer is what was actually the energy emitted by this event? And that we can determine by essentially making simulations. So people are trying to just calculate the wave that is emitted by different constellations. So it's in some way reverse engineering. You just try out different things. You just check what happens if a, let's say, 20 solar mass black hole collides with a 50 solar mass black hole with a particular angular momentum in between them and so on. And then you calculate what are the gravitational waves coming out of that, what's the signature of that, and you can also calculate now how much energy was lost by this object. And now you do that just for many possible constellations and compare the actual signal we have to that. And from that, you kind of now make an estimate. And I think there was a particular estimate for the event that was detected, for example, where I think the waveform just corresponded to having one of the original black holes. Okay, now I don't remember the numbers exactly, but I think they were of the order of 20 or so solar masses, the other one a bit heavier. And if they were different, this would have led to different waveforms. And the wave is, of course, the real wave is much more complicated than this, because as I said, the whole duration of the event is only 0.2 seconds. And we have something of the order of 200 hertz, 50 to 200 hertz. So if you have 50 hertz, this means we have only 50 oscillations in a second. So in this fraction of a second, we maybe have only of the order of 10 oscillations. And they, of course, raise in amplitude as the whole thing collapses. So it's a very complicated shape and a very complicated dependence on the event. And so it's really numerics that allows us at the end to make this connection between the actual observed waveforms and the possible, let's say, astrophysical processes that went on when these black holes merged, which you do just by simulating the Einstein gravity. I hope that's fine as a twofold answer in that sense. Okay, are there other questions, Louis?
Can I ask a little question? If I remember correctly, in our electrodynamics class, so it wasn't with you, but I think our teacher said something like that gravitational waves are quadrupole waves.
Yes, that's right. Yes, absolutely. Okay, that's a good point. Let me maybe briefly make a comment on that one. So I didn't say that here, but this tensor here that I wrote down has some additional constraints. So not every choice of these H0s, H1s, and so on, and every choice of phi's would be a valid solution. It actually turns out that the divergence of this whole thing, as well as the trace of this, are both equal to 0. So you have only, in a sense, 2 free parameters left, because there are originally 4, and then you reduce it by the divergence and trace roughly. And so they are. So if you think of this as the trace being 0, then what it means is that if I draw now a picture of how do the distances look like. So I have before these 2 arms of the interferometer. Let's say this is again P, that's Q, and that's Q prime. Okay, I think I drew it downwards. So let me try to be consistent here. So there's Q prime here. Now, an exaggerated picture, which is, of course, I will not draw on the level of a fraction of a proton radius, would be the following. So let's suppose that's the situation without gravitational waves. So we could draw kind of a circle here. Now, as the wave, and now, okay, comes a wave in, And if the trace is 0 of this tensor that you see here, this means that if one component here becomes shorter, then the other one here becomes longer, but the sum will remain the same roughly on this level. So if you turn this into distances, which are the square of this whole thing. Oh, by the way, I think the distance, I forgot to say, to put the square root. I think I should really do that, because the distances are, of course, at the end, the square roots. Anyway, so if you put the distances into a diagram, you could say, okay, if this thing becomes shorter, so it's a square is of a certain size, then the square of the other one has to be such they add up still to the same thing, because the trace has to be the same. So at some point they will look like this. That will be a possible shape as the gravitational wave passes. And then maybe let's say a hundredth of a second later, if this is 50 Hertz, you would have a shape like this, where this is much longer, and Q prime. And so I just draw here, so this will become an ellipse in some way, and here as well, but one with the opposite thing. So the gravitational wave is, it's like something that squeezes a circle. So it squeezes and it extends on the other side. And that's really the signature of, I mean, mathematically, that's like what you have when you, for example, calculate the quadrupole moment or so of an electromagnetic wave. So that's a tensor, because, I mean, maybe you remember in electrodynamics that is what was also a symmetric tensor. So it has this tensor form, and so a contribution so by definition, a contribution that is trace-free and divergence-free is called a tensor contribution. And it turns out that the lowest order contribution is such a tensor contribution. This is different from electromagnetic waves, where you also have dipole radiation. But because here we have a priori this tensor, okay, that's maybe not the only reason, but I mean, at the end, the calculation we will do, or you will do with the exercises, shows that it really has this form, and you could, in principle, calculate these properties that I mentioned, trace freeness and divergence freeness, and which correspond exactly to the corresponding conditions you would also have in electrodynamics. So yes, the answer is therefore yes, that's true, and I try to give you a reason, or try to give you a picture of what that means in practice. It really means that it has this behavior here, and I mean, it kind of oscillates between the two situations. Of course, that's in some plane, and one has to be lucky that the interference arms are just directed in the right plane where this happens. This will not be perfectly the case, but the idea is that we have several interferometers on Earth, and then we kind of get a coherent picture by comparing their results.
Okay, thank you.
You're welcome. Okay, if there are no other questions, okay, it's not yet 5. Oh, no, it is. Okay. Are there any remaining questions about gravitational waves? If not, I would like to start with a last or second to last topic. So maybe you remember I mentioned last time that in this week I wanted to do some applications of GR or an outlook, more speculative parts. And one thing I want to do is to give you an outlook on cosmology. That's of course a separate huge topic, and I will not attempt to cover it in any way. I just want to make or give you some information about what this would be like if you continue studying GR in the context of cosmology. What is the connection to GR? What can GR tell us about cosmology? And then also on Thursday, I will give you an outlook on connection to quantum mechanics. That's what I also mentioned. By the way, this is maybe a good opportunity to also make you aware of another special tutorial that we are going to have this week on Friday at 3:45 after Julia's tutorial. Jan Zosso will talk about the foundations of Einstein gravity, which is a research topic he has, and where he looks at the whole thing from the QFT, from the quantum field theory perspective. I think I mentioned several times that there are alternatives formulations of gravity where you don't use the Levi-Civita connection, but somehow try to represent the actual physical objects in a different way. Still a differential geometric way, but a different way compared to how we did this. Ours is the standard one. And this gives some interesting insights. It also, for certain calculations, is advantageous. And he will show how, if you combine this with quantum field theory, you can do interesting calculations and get interesting insights. The talk will certainly be accessible. So he's, of course, very well aware of what you learned in this course. And I'm sure this will be a very nice opportunity for you to see what it would mean to start research in this field. So in case you decide to stay in this area, at least in a theoretical discipline. Okay. There's also, if I'm about to make announcements and so on, there's one more announcement that I would like to make, which is that I received the lecture evaluation back. So I would like to thank you very much for actually giving feedback on the lecture. This was very useful feedback. There's not much that to say about it, or not much that you want to change, but I received comments of the type like, this lecture should be more mathematical. And then I also got some comments, oh no, this lecture was too formal. And luckily there was also some comments saying it was a good balance. So it is true that one has to make a selection. So this lecture cannot cover a full, or cannot be a fully rigorous treatment of GR. That would include building up the whole differential geometry from scratch, which by itself would fill more than one lecture. On the other hand, we have to understand differential geometry well enough to be precise. So the philosophy I followed, maybe I should say that one more time just to make clear you understand the choices I made. The philosophy I followed was that in order to understand physics, we need a language. And the language is, of course, mathematics. And in this particular case, it's differential geometry. Now, in order to make sure you can really work on a topic, you need to be very good at the language. So I tried to be rigorous enough and precise enough so that you really understand what the basic concepts are. And these are, of course, mathematical concepts like tangent spaces and so on. And on the other hand, you need to understand how they relate to physics notions, that a vector in tangent space corresponds to a direction in space-time and so on. At the end, the course can only cover a small part of all that, but I hope it achieved at least the goal that you are now able to, that you now have the language learned to be able to read both mathematical literature on the subject and also read physics literature. So somebody should have given you the skill of now going on and do whatever you like, go more in the rigorous direction or go more in the physics direction. And I'm sure you now have a very good basics for that. If you know these concepts well that were introduced, then I think you essentially got the way of thinking in this field. And of course, there's a lot to do with them. There's an enormous amount of literature and stuff that has been done. But you can now choose, you can now read all that. It's a bit like in many other disciplines. When you learn something, today there's so much information about, you have to have the ability to judge whether this information is good or reliable, but you also have to know the basic concepts. And that's how I made the choice. Anyway, that was one of the, let's say, only points that was criticized. I was, of course, glad to hear that you liked the course. I would also like to thank in this context the teaching assistants, because it was mentioned several times that they gave excellent tutorials, and I'm really happy about that. Okay, by the way, if you want to know more details about the lecture evaluation, I just put it on the Moodle page. You can download it here and look at the whole statistics in case you're interested, and also read the comments. Okay, so that was the other announcements. Oh, there's a last announcement, and then I really continue. Some of you asked me once, I think I once made a comment about the relation between general relativity and quantum mechanics, which we will of course discuss on Thursday. And in this context, it's of course an interesting question whether, I mean, if you ask, is relativity theory consistent with quantum mechanics? This is in some way a question that only makes sense if we can say that general relativity theory itself is already a consistent theory and quantum mechanics itself is a consistent theory. Otherwise, it's not a surprise that if you combine them, you still get an inconsistent theory. For example, quantum mechanics was already by itself inconsistent. And by coincidence, I was asked to give a presentation about the consistency of quantum mechanics tomorrow afternoon at 3 o'clock. This will be a kind of science talk, but it will certainly be accessible. And if you're interested, you're welcome to join. I will put the corresponding link, the Zoom link, on the group webpage, qit.ethz.ch. Okay, now.
Yeah, there was another question in the chat.
Oh, yes.
There is somebody asking, can you say something more about the exam? How will it be structured?
I would be happy to do that, but let me do that on Thursday, if you don't mind. Because I also want to first have a discussion with the teaching assistants. Again, we are currently planning the exam, then I can give you much more accurate information. I hope that's fine. Okay, now, as I said, the chapter, or it's not really a chapter, it's, as the title says more, let's say, a small section with an outlook to cosmology. Cosmology is a scientific discipline nowadays. It wasn't always so, but actually thanks to Einstein's field equations and the whole GR, we can now reason in a very precise way about the universe. Of course, the underlying assumption is that the Einstein field equations and the whole concept of GR apply to the whole universe. And cosmology is really about the universe, about how it came about, how its future looks like, and so on. Now there's two things I want to tell you, and the first is, I mentioned several times that there is a cosmological constant in the Einstein field equations, and this is not surprisingly relevant for cosmology. So let me first make a few comments about this constant. And for that, it's useful to recall the action principle that we had. And I will now, don't worry, I will now not go into the details again of the action principle. I think we discussed it at length. But what you should remember is that it's essentially a sum of individual actions that we define. So we said the total action of a system, which is now the whole universe, is given by the Einstein-Hilbert action, which is this 1/16p g Newton, and then the integral over the Ricci scalar omega g, and then plus some matter action, and this really depends on the matter. I will not write it down, but I gave you the example of the electromagnetic field. But now we can add something else. And why can we add something else? I mentioned several times that there is not so much degree of freedom. So it's actually hard to come up with some expression like this one, which is a scalar that is independent of coordinates. And of course, R, the Ricci scalar, or the curvature scalar, is a scalar. And so if I integrate it over volume, it's a well-defined physical number, but there are not many of them. But one we still have, I mean, what's a number that is well-defined, somehow coordinate independently? Such a number is just, I mean, if I choose a constant, then of course that's a coordinate independent number. I can just say, instead of R here, we could have integrated over some constant. And the constant is a scalar, and therefore this would be also something well-defined. So let's do that. Let's add a term, which I call now cosmological, here S cosmological. And it's really exactly what I said. It's just 1 over, and now there's, for conventional reasons will be some factors, but let me maybe put the factor only in the integral. We put here 2 and then a constant, which is now the cosmological constant, and we integrate with the volume form that is induced by the metric. I mean, that's a well-defined thing, at least mathematically. That's well-defined in the sense that it's coordinate independent. People are often putting these two things together into one action. I call this S lambda, because of course it depends on how I choose this constant. And then the action obviously looks like this. I have the curvature scalar plus 2 times this constant that I just introduced. So why should we introduce it? So at this point, the answer is just because we can. There's no reason why it shouldn't be there, and we can still set it to 0. And if you are really taking this way of thinking, saying, let's just put everything that is mathematically consistent. As I said, there are not so many things, but this is certainly something we can do. So let's just put it there and then a posteriori see whether this term maybe disappears or remains. Of course, in this case, the answer will be it remains. So it turned out not to be a bad choice. Now, what does that mean? Of course, we can turn this all in an equation, and to see how this now enters the Einstein field equation, remember that we got the Einstein field equation by varying the action with respect to the metric. We already did it for this part. We also did it for the matter part. Now for the cosmological constant part, this is quite easy because obviously it's just a constant. So varying it is not that hard. So we could just say, let's take the variation of this term. Okay, maybe I'll just use here the fact that we already defined it. So I take the variation of this term. And one way to do the variation is to essentially take it into the integral. So let me maybe first write it still outside. So remember that if it now work in coordinates, I can say I take the variation with respect to Gij, the reverse metric. That's the same that we did when we derived the other terms of the Einstein field equation. And then I have this whole thing. I will just get rid of the factor 2 here in front. So I write just 1/8 times g Newton. And then we have this integral over lambda. And if I'm in coordinates, it looks like this. Remember, that's what the volume form means. It's the determinant of the metric and then the square root of it. Now, as I said, we can take this variation inside the integral. And if we do that, we get obviously a term or a term of this form where we take the derivative of the square root of the determinant of g, which we already evaluated, I think, a week ago. And I just remind you of what the result was. This is something you can look up. I think we already used it at least twice. So if I put that into the equation again, the minus is here, and then I get a 1/16 pi gn. And I still have the integration, the constant remains. I have now a Gij, and then I can again write, it's just the volume form. That's what this square root of the metric means times d4x. So now, as I said last time, the Einstein field equations are the sum of the variations of those. So actually the reason why this works is that if we take the variation of the total action by the rules of taking derivatives, we can just add the variations of all the individual terms. That's just the addition rule for taking derivatives. So we can use whatever we did before. We already know this variation, we know this variation, so we can just add this term. And what we get if we do that is the following. So if I now vary the whole term d, okay, now okay, I think I made a mistake here. This was only the lambda term. Let me correct this. So this should have been, I only vary actually the the orange part. That's what I did here. But now what I want to do finally is to vary the whole action is lambda. And if I vary the whole action, as I said, the terms just add up. So the term that we get usually from the Einstein, from the variation of this part of the Einstein-Hilbert action was just the Einstein tensor Gij. And now we got this additional term here with a minus of lambda. So we get lambda Gij. And then omega g. So that's what we get if we vary here. Now, of course, the Einstein field equations arise by setting the variation equal to 0. So if, or equal, yeah, okay. There would also be the term of the matter. So we set it equal to the variation that comes out of the matter. But remember, the variation of the matter term just gives the energy momentum tensor. So in other words, if I set the variation to 0, then it means that I get the following, which are of course now the Einstein field equations. So I get this term that is in the integral. The integral can only be 0 if for all variations if it's 0 everywhere. And on the other side, I just get 8 pi g Newton Tij. So that's the term that I now didn't put, but that just comes out of the variation of the matter. So these are the full Einstein field equations if we include in the action this additional term here that I introduced. So actually there's nothing different from the derivation we did before. I just added this and now we got this additional term. Now it's tempting and maybe also not a bad idea to say that this term that we introduced could also be moved to the right-hand side. Why not? So we have here 8 pi g Newton Tij, and then I just put here plus lambda Gij. And now it's a bit like a matter part. So you see here we have still the geometry part, the Einstein tensor, which essentially consists of the curvature of the Ricci curvature minus the scalar curvature times the metric. So that's pure geometry. And on the right-hand side, we have the actual matter. So this is, for example, particles or also electromagnetic radiation. And now we have this additional term. So what's this additional term? We don't know. And that's why we call this term here dark energy. So that's what in GR, what it means in GR to talk about dark energy. It's the term that comes from putting a actually positive cosmological constant. Of course, this gamma has to be lambda has to be non-zero, and then we have this additional term, and it has somehow a similar effect as matter because it's now just seen as something of the source side of the Einstein field equation. So it contributes in addition to the curvature of space-time like matter does. But it's not matter. We don't know what it really is, but it somehow contributes to the curvature. Now, by the way, this is not the same as dark matter. Dark matter is still matter. So when people talk about dark matter, they mean somehow particles or maybe stuff that is a bit like radiation, but things that behave in principle like the particles that we know, just undetected particles. So that will be included here. But this term here is different, and I will just show what the difference is. It has somehow a behavior which is still in a way very different from that of matter. So when people talk about dark matter, they may mean a contribution to here. When they talk about dark energy, then it's this cosmological part, this cosmological constant part, the Einstein field equations. Maybe you know from talks that are often given that this is at the end a relevant contribution on a cosmological scale, because 74% of the kind of density of matter, if you put everything together, comes from here. And by the way, 22% comes from dark matter. So it would be that T that we don't yet know. And only the rest, I think 4% or so, comes from a T that we know. So the Einstein field equations make it very clear that most parts of the universe we don't know. But how do we still know that they exist? The reason is that we know the left-hand side, that's the geometry. So it's actually the Einstein field equations that give us at least some access to these dark parts. If you didn't have the Einstein, I mean, there are of course other conjectures you can make about things that have to be there, but the Einstein field equations give you an actual access to stuff, because you know this, you can measure or map out the geometry of space-time in principle. I mean, that's of course very hard in practice, but you can do it to some extent, and then compare it to all the matter that we know, and then realize, oh, there is something missing that should have the same form as that. So that's dark matter. And then there's still something missing of that form, and that's dark energy. Okay. So you see, the Einstein field equations are in that sense an enormously useful tool. I mean, more than a tool, it's kind of maybe even the basis of modern cosmology. Now I want to maybe briefly discuss in what sense this is really different from that term. So remember that we looked at dust, and the dust energy momentum tensor was basically a tensor which had the form rho times u I uj, where u is the velocity, the forward velocity of the dust. So I assume that dust consists of particles which are all moving roughly in the same direction, and u is rho is the density of that dust, and u is that direction in which they are moving in space-time. Now, if they are slow, then this u is approximately in an appropriate coordinate system. If I take space-time and Cartesian coordinates and so on, has the form that it's 1, 0. I mean, if it's exactly not moving, it's 1, 0, 0, 0. If it's moving at a small velocity with respect to the coordinate system, to the 0 point, then this u is something like this. Of course, you know it's not precisely like this. There are also these prefactors, 1 over square root of 1 minus v squared and so on. But that's a good approximation of how this u looks like. So why am I telling you that? So if I now write down explicitly the components of Tij, you see that we have here in the first, I mean, first of all, we have a rho. I could also have put the rho here, but I put the 1. Everything is multiplied with rho. I have a 1 in the upper half, and then the u0 uj contribution of the term. So if I, for example, look what is here, then there's a u0 and a uj for j not equal 0. This gives just a vj contribution. So here I have something like v1, v2, v3, where this is the 3 velocity. And of course, the whole thing is symmetric. So it looks like this. And then in the lower part, I have stuff. Okay, I will not fill out everything, but you see there are things like this v1 squared, v2 squared, v3 squared, and then there are also some mixed terms here which are can easily add. However, there is now something that you may notice. Suppose that we have particles which are not all moving in the same direction. So here we assume that there's just some density and all the particles are roughly moving in direction u. Now I could have some particles which are moving a bit to the left from my perspective, some that are moving a bit to the right, both with slow velocities, and they both, I mean, if I now want to take this into account, I have for both types of particles, the ones moving right and the ones moving left, I have an energy momentum tensor, and I can just add the two energy momentum tensors of the two. But if I add them, then certain terms will cancel out. So let's suppose that I choose the coordinate system in such a way that the average movement of the particles is 0. So if I average over all velocities, I get 0. So if I now look at that, so T average in that sense, so I told you what it means. I have all these particles moving in different directions. How does it look like? So this one, of course, doesn't go away with the averaging, but all these terms V1, V2, V3, because they have a sign, sometimes it's positive, sometimes negative, this will go away. So in the coordinate system where everything moves in such a way that the average speed is 0, not the individual speed, then it's that. So that's a bit like a gas. If I take a gas, of course, if I average over the speed of all gas molecules, it has to be 0. Obviously, because otherwise the whole container, I mean, if I have a fixed container here on my desk with gas, the average speed of all the molecules is 0 with respect to this container. Otherwise, the gas would somehow move out of the container, or the container would start to move. So these cancel out. Also, all these terms here in the off diagonal, because they have always a V, for example, that's V1, V3. So if I change the sign of one, this cancels. But what will remain are these square terms, because here the sign doesn't cancel out. And so the energy momentum tensor of matter that consists of things moving in different direction, therefore has this form. Now, if you look in statistical mechanics, classical statistical mechanics, if you have particles moving, and if the total, so let's suppose we are somehow isotropic, so we don't distinguish one direction. So these squares here in the diagonal should all be equally large. This is, of course, the case if you have a gas. There is not one direction in which things move faster than in the other direction. Then these terms all correspond to the usual thing that you would identify as the pressure of a gas. That's just kinetic gas theory. So if you take as a model of gas particles, little particles with mass m and the velocity v, and you average over all of those and calculate the pressure, then you will see that the pressure is essentially is equal to the individual terms, assuming that they are isotropic. So we could write something, actually it's rho times, so the pressure is this times this, so the full diagonal corresponds to the pressure. And that motivates a tensor that I've already introduced at some point, which is has this form where P is the pressure, and we have no off-diagonal elements. And that's called a perfect fluid. So that's what in relativity theory, when people talk about a perfect fluid, they mean this energy momentum tensor. And I'll give you motivation of what it is. It's essentially something you can get from kinetic gas energy of an ideal gas. So an ideal gas is in that sense a perfect fluid. Okay, but now we can compare it to the, so that's kind of a very general way of how matter should look like. And actually most of the matter, at least if it's not too dense, like if the ideal gas approximation works, which is probably the case for most parts of the universe, I mean, that we know, and then we could say that it should have this form. So all the known matter, the part that is here, could be well approximated by this. But what about this additional term, the dark energy term? So the dark energy term that you see here is a constant time Gij. So again, if I'm in Cartesian coordinates, then lambda times Gij looks like this. It's just, of course, lambda, minus lambda, minus lambda, minus lambda, because that's the signature of the metric. So it's like a perfect fluid with the property that rho is equal to actually gamma. Okay, I need to normalize it, 8 pi gn. Why this normalization? I mean, if I want to see it as a, okay, let me do it in the following way. So I want to put it into the form of a tensor. Now, if I want to put it into the form of a tensor, of an energy momentum tensor, here we have no prefactors. So I somehow would better include the prefactors here so that if I multiply them again, if I see them as a tensor, that they cancel. So that's why I put here in this equation that I'm going to write down this prefactor. So the rho is lambda over 8 pi gn. But P, that's now the interesting part, is minus lambda over 8p gn. So it's as if we had a, and that's of course minus rho. So it's as if we had a perfect fluid with negative pressure. So dark energy is in that sense really not matter. It's something with, if we just use that as an analogy, would have negative pressure. Now you can ask me, what does this mean and so on. Of course, it's just an analogy because here we have these square terms that will never become negative, obviously. It's just saying that this term that we added, that just comes out as a natural additional term, cannot be seen as particles that move around like a gas. So the whole point is they are not particles. They are something really different. And in that sense, that justifies also this distinction between dark energy and dark matter and normal matter and so on. Okay. Now okay, that was one part of what I wanted to tell you. That's kind of the beginning of how cosmologists start to think about the Einstein field equations. So first of all, need to know what is the most general form of it. And it's clear that cosmologists are interested in including such all the terms that may be there, and then kind of doing measurements, in actually real measurements, and figure out whether the terms can be supported experimentally. And of course, the measurement could now show at the end that there is just no such term that could have happened, but it didn't happen. Because if you now really do cosmology and try to measure out G, you will find that you need this term, and you can estimate its size. So cosmologists in that sense determined indeed that the Einstein field equations need to have this form to match experiments. So they are really these or these equivalently. And we also know how large this term is here. Okay. Now, it's probably unclear how cosmologists could arrive at, how could they map out space-time and so on to determine these quantities. And that's the next thing I would like to do in the last 10 minutes or so. I would like to explain to you something that is called the standard cosmological model. And in a way, you can just regard this as an enormous simplification of the Einstein field equations. So the Einstein field equations are hard to solve. I said that several times. If you now want to solve them for the whole universe, that's hopeless. So you need to make certain approximations. Now, the approximations that cosmologists make is to say that the universe is spatially homogeneous and isotropic. So what does that mean? They just somehow take the view or the same approach that we do when we do thermodynamics with a gas. Of course, if you look very closely what the gas is, then we see individual particles. And clearly a particle is, I mean, at least in classical mechanics, either here or here. So there's no homogeneity. So things look different here and here, or here I have my table, and if I step to the right, there's something else. So space is not homogeneous, or the whole, I mean, space and the whole configuration of matter. But if it zoom out enormously, so we have to zoom out so that not only solar systems disappear with their structure, but whole galaxies somehow just get lost in the coarse graining that I'm doing, then at the end there's just one uniform mass somehow there. That's of course an enormously far-reaching assumption. And in addition, it's also assumed that it's isotropic. So in whatever direction I look, there's no preferred direction, or everything looks always the same. But this is spatially. So it means, so implicit to this assumption is that we have somehow a space direction compared to a time direction. Now, formally, what that means, and we can now understand what, I mean, of course, that's just nice expressions. What does it mean formally? Formally, this can be expressed in the language of Killing vector fields. So what is a Killing vector field? Just as to remember, those who did the exercises are, of course, highly familiar with the concept. It's essentially a vector field such that if I take the Lie derivative of the metric, it disappears. So what does it mean? It means that a vector field, or maybe remember, a vector field is associated to a flow. So there was a time when I talked about lying on a river and looking at the sky and look how things change. And the river, the flow of the river is defined by a vector field. Now, if I'm floating on the river and look at the metric, then it may be that the metric never changes as I'm floating. And homogeneous means that there are always three directions in which I can float, namely the three spatial dimensions, such that the metric doesn't change. So the idea is that P1, there are three directions, so there exist three such fields. These are vector fields, but you should think of them as flows into the three possible spatial directions. And also the isotropy means I can rotate, and I can of course also rotate in three directions. So there exist also three vector fields that somehow correspond to rotation. These are again vector fields, which are all, they're just all Killing vector fields. So maybe I could just add that here. So there are three directions in space in which I can move, and three types of rotation I can do in such a way that the metric never changes. So everything, so the geometry remains the same. So now, when I say there exist three fields, what does that mean? Because one has to say that in a general way, in a coordinate-independent way. And the way this is usually done, this is just for you to, I mean, we will not do calculations based on that, but just to make you aware of how people think of this, you just look at essentially the commutators of these vector fields. And of course, you know that, for example, if you rotate around J1 and then J2, then this is the same as, and then do it in the opposite order, backwards, then it's the same as rotating around J3. So you define the vector fields that correspond to a rotation by their commutation relation. Of course, for the vector fields that correspond to just translations, which are the p vector fields, the idea is, okay, here maybe I'll just write it directly. The idea is that they all commute. So if I move in different spatial directions, this is all zero. And then there's also a connection between rotation and moving in space. So if I somehow rotate around one and move in the direction P2 and then do it in the opposite order backwards, this is like moving in the direction P3. This is again plus cyclic and actually also antisymmetric variants of this. So this is just how this is modeled. So in other words, people are saying our assumption that I put here as a, let's say, in words, means that there are these vector fields corresponding to spatial translation and rotation defined in terms of their commutation relations, which are all Killing vector fields so that the metric doesn't change. So it really means as I move, if I do a translation in space, And this defines what the translation is in space with respect to the other vector fields. So there's not a priori what space is. This is defined implicitly via these commutation relations. But if I then do a translation, the metric doesn't change. So that's what it means to be homogeneous, and the same for J for the isotropy. And now symmetries usually allow for an enormous simplification, and the simplification that one gets in the case of us making these assumptions is that the metric of the universe is now very simple. So first of all, it has to be the same everywhere. That somehow follows from the assumptions, but it has to have the following form. The metric has to have the form that is a 1 here, and then in appropriate coordinates. So the statement is there exists coordinates in which the metric is such that time is just such that there is no scaling. And then there is here another matrix called gamma ij. And this matrix depends on a scale factor, which is denoted by A, which may change in time. And in our convention, we put them always spatial matrix with a minus. It has to have this form. And this is there. Now I have to say what is gamma. Gamma has now nothing to do with the gamma that we introduced in the context of gravitational waves. So we are now in a different chapter. Gamma is the metric of a spatial or maybe I write it like that, of space with of 3 space, that's just in the 3 space part, with constant curvature. Kappa, which is, and kappa could be either 1, 0, or -1. So what does that mean? So a space with constant curvature 1 is essentially just a sphere. A space with constant curvature 0 is just a plane. And a space with constant curvature -1 is essentially hyperbolic. So it's consisting of saddle points everywhere. That's the way you can think of it. So what the cosmologists tell us is the following, that if we assume that the universe is completely homogeneous and completely isotropic, then the metric everywhere has this simple form. So the only parameter that is left once you fix whether kappa is 1, 0, or -1 is the scale factor A. So that's, before we had, of course, an arbitrary metric, and now we reduce the metric via the symmetries to one which has a scale factor. So this scale factor somehow relates how large is space depending on time. And now I think our time is over, so maybe I'll have to finish that discussion on Thursday, because one of the comments in the teaching evaluation was that I should really take the break seriously, and I think this could be a break for someone who has another lecture. So I will stop in a minute, but let me at least again comment on that result. So by the way, this has a name. That's the Friedmann-Lemaitre-Robertson-Walker metric, also sometimes just called Friedmann-Robertson-Walker metric or Friedmann metric and so on, depending on whoever we want to give credit. But it's essentially a very simple model of how the universe looks like. So the universe is a completely uniform mass, and it's somehow the only interesting property is that space has a scale factor. That's this AT. AT is a function, so space can become larger or smaller depending on t. That's the thing here is constant, so that's something you fix. This kappa is just, you say the space looks like a flat plane or like a big sphere or so. So actually, maybe you can just assume it's flat for the moment. And then this whole thing just tells you somehow the universe must be such that space is always there over time. Everything is constant, but maybe spatial distances grow. And maybe I will spend on Thursday still a quarter of an hour of that, because if you now want to find out what is A, we have to solve the Einstein field equations. Of course, I mean, that's what cosmologists do. I will just tell you the result, but the result essentially contains all the things usually hear about. So for example, one result will be that A of t is such that A becomes very small in the past and goes to zero. That's of course the Big Bang. So the Big Bang corresponds to a situation where space was so small in the sense of this scale factor that it was all, I mean, its total distance approached zero in the limit. And then it started to grow. So it's the whole space that grows. So if people usually say in the Big Bang space was created, that's really, this metric is what this means. There was, if A is zero, there is no space. There's no spatial extension. And then A starts to grow. So space is kind of created. And now you can ask, does this A continue to grow forever? Does it even grow in an accelerated way and so on? And these are questions that cosmologists ask. And as I said, I will maybe spend a few minutes next time giving you an overview of the answers cosmologists have about what is now this term A and what does it mean. Okay, that's it for today. Thanks a lot for staying.